I'm Andra, and together with Stefano today, we'll be talking about virtio-vsock in QEMU, Firecracker, and Linux. I'm working at Amazon, and I'm a software development engineer there, and I'm working mainly on the EC2 infrastructure, on the Nitro and Xen hypervisors, where Nitro is based on KVM. And Stefano, please.
And I'm Stefano. I'm working at Red Hat in the virtualization team, and virtio-vsock is one of the topics where I'm working on.
Okay. So let's further see what we'll be talking about today. We'll be talking why we'll need to have the virtio-vsock implementation, several use cases, and then go through more into details of the backend, and which are the updates on the Firecracker, QEMU, and the Linux kernel side, and which will be the next steps. So first of all, let's see, we have this diagram where we show we have a guest and a host, and we have an application on both ends. And we would like to have a local communication channel between the two. So we can use a network device there, and we'll need, for example, to set up the IP address and also the routing. And we can use the socket API, while the addressing will be the IP and port. So why not instead have no configuration regarding the addressing and port and routing, and use instead the virtio-vsock device? What we need to change from the app perspective is the addressing. So we maintain the same socket API, but we have now, instead of the IP, the CID, the context ID. In the guest and the host, we need support from the kernel side. So on the guest side, we need to have virtio-vsock support, and on the host side, we need to have vhost support. And the device that is available on the guest side can be either MMIO and PCI, or PCI. It's available to the guest to choose what will be available there. And next, several use cases. We can have guest agents or hypervisor services. And for example, we can have file sharing, log and metrics sharing, and see which are the updates on this side and which is the behavior of the guest, for example. And talking about the socket API before, we can have network applications. But we can move these applications from a network device to a virtio-vsock device in a seamless way, because we do not need to change how the API is called, but only change the addressing. We keep the port, and now we have, instead of the IP, a context ID. And now, until now, we've been talking about a communication between the guest and the host. Why, if we need a communication between two VMs? We can get that, but we will need to have additional implementation on the host side. So we can have the routing done, or we can have shared memory between the VMs, and this can be done seamlessly. Next, few more details. So let's dive deeper in how the backend looks. From now, we've been looking from the host and guest perspective, and how the application looks, and which are the needs to do, or which needs to be done to have the changes from a current implementation and port to a virtio-vsock implementation. So in this perspective, there is the host that needs to have support for virtio-vsock. That's mainly the vhost-vsock implementation. And we have upstream available support for NET, for SCSI, and for vsock. So how will this look, the entire communication and the setup of the device? So first of all, we need to set up the device. We need to have the interaction with the VMM so that we have the configuration done. And then the data can flow without the need of the cooperation from the VMM, because the host has access directly to the buffers from the guest. And for signaling, we'll use event FDs. So when the guest has some data for the host, we'll signal using IO event FD. When the host has data to send to the guest, we'll signal using IRQFDs. And this all works after doing the setup of the device, and we can send data in this way. And we can keep the application using the same API. But we need support from the kernel drivers. Next, what's available in Firecracker? So Firecracker, there was a talk before about Firecracker, but in a nutshell, there is an open source VMM. It was released the previous year at AWS reInvent, and it's used in the internal infrastructure by Lambda and Fargate, and externally by Kata containers, for example, because they use, in addition to QEMU, also Firecracker. So let's say we have a function or a container task, and we want to run this in an AWS infrastructure. A VM will be launched, and this VM will use the VMM that it's using the Firecracker implementation. And regarding vhost implementation, it was available as experimental till v0.18. But why we need to move to another implementation? Because at that time, if you want to have support for virtio-vsock, you need to specify this in the build time, at the build time, because it was not available by default. You need to specify this as a feature, and then you'll have the possibility to add the virtio-vsock device to the VM. So we moved from this implementation with vhost to an implementation using Unix domain sockets. And why Unix domain sockets? Because we maintain the same socket API, so we keep the same logic, but we'll have like different, now we are using a path instead of an IPM port. And why we need to move from that implementation to the one with the Unix domain socket? First of all, it was the security impact. Before, we've been talking about the host having direct access to the guest, to the buffers. So there could be an issue in the vhost driver. So there could be also a privilege escalation from this perspective. So using the Unix domain socket instead of the vhost implementation on the host, we can this way reduce the security impact of what could happen if there is a security bug on the guest side or on the host side. And for example, there was a recent CV regarding the vhost kernel implementation when there was a buffer overflow, and this could lead to privilege escalation in the guest. So this is from the security perspective. Now from the functionality perspective. What if we need to have, by default, the vhost implementation on the host? We would not want to have that, and this way we reduce the code base or the available functionality that needs to be there to have a proper communication between the guest and the host. And the virtio-vsock device model is now available in the VMM, in the Firecracker VMM, and on the host side we only see the Unix domain sockets path. What we need to do for configuration? So we will have one virtio-vsock device per VM. So that's the available implementation in Firecracker. And till now, we've been using QEMU. And we have a guest CID that needs to be set up there. In addition to that, we now are using a Unix domain socket path. And the VMM is listening by default on that Unix domain socket path. And the vSock connection can be established from the guest side or from the host side. So we have these possibilities on both ends. Next, let's see how this works from the host perspective. So let's say we have a host and it wants to connect to the guest. We have in the guest side an application that listens on a certain port and is using a virtio-vsock device. On the host side, we have an application that connects to the Unix domain socket path that was configured at VM launch. Nearby, something needs to do the mapping between the two connections. Here comes Firecracker, where we have a vSock endpoint with the CID of the host, that's 2. And we have a Unix domain socket path, the one that was configured, and I was mentioning before. And the VMM is listening on this socket path. So the connection mapping is done between the two. And when the host sends data to the guest, before that, it needs to send a special message that connects to a certain vSock port, because the application is listening to a certain port, and Firecracker needs to do the mapping between which socket path from the host is going the data to which endpoint on the guest. After we have all the setup done and the connection mappings are established, we further can send data without the need to have other things different done than it was before. So we can use the same socket API. Then the other way around. From the guest, we want to connect to the host. So we have an application that connects to CID2 and a certain port. And then on the host, we need to listen to a certain Unix domain path. But now there is a different Unix domain socket path, because we need to identify that specific connection with that specific port. And for now, it's the Unix domain socket path that was configured at VM launch, together or appended with the port that the vsock application connects to. And in the middle, Firecracker also has the vsock endpoint as before, and it's acting like a host. And then is the Unix domain socket path that is used to connect to the host that is listening on that path. And after that, we do not need to have an additional message sent as in the previous example, but can send directly data from the host to the guest application and the other way around. Talking about guest to host implementation. Now let's see a few of the metrics, because we've been looking on the throughput side, and we've been using iperf and a socket on the other end. So we have a VM that's running on a metal instance, and we are looking on the user space buffer side that is sent to the iperf, and also on the throughput that we gain when we send data from the guest application to the host application. And here you can see a connection takes buff size mentioned in the legend. So that's the buffer that is used by Firecracker to get the data from the virtio-vsock device to the Unix domain socket device. And why we need this kind of buffer? It's a simple ring buffer. That's because we need to actually take the data from the virtio-vsock device and send it to a buffer if we cannot cope on the host side to receive the data immediately on the Unix domain socket. So we are looking on this from this perspective and from the perspective of a buffer user space from the iperf side. And we can see that growing the user space buffers and also the takes buff size, we see a growth from few megabits per second to 10 gigabits per second. And that's the implication of what will be needed to be done on the vsock side and also on the Firecracker VMM side, so that we can send the data between the guest and the host. So just to sum up of what we've been done until now, Firecracker has available since v0.18 the virtio-vsock device implementation. It's using the Unix domain sockets. And you can get it, you can clone it, and you can check it out on a KVM-based box, because it's available out of the box, and you can get it run and get us your feedback, so that we can see what we can improve on that side, and also what we can do further from this perspective. And now, let's move further to what is needed on the QEMU, on the Linux kernel side, which are the updates and the performance there, and which will be the next steps. So Stefano will take the stage now.
Okay, thanks. Let's talk about QEMU and vsock. QEMU provides the virtio-vsock device using the vhost vsock kernel driver. So the device in QEMU handles only the configuration and the live migration. It allows the user or the management tool to configure the guest CID and to migrate a VM that is using vsock. In this case, connected stream socket become disconnected, and so the application must handle a connection reset error and should reconnect. And the guest CID cannot be available in the new host because, for example, is assigned to another VM. In this case, the guest is notified about the CID change. Most of the work in the host is done in the vhost kernel driver. So it handles the communication with the guest, I mean the virtq operations, providing in kernel virtio device emulation. This allows us to have better performance. And in addition, the vhost kernel driver implements the interface with the host socket layer, allowing a user space application to use the socket API with the vsock address, with the vsock address family to communicate directly with the guest. So in the QEMU KVM environment, we use two vsock transport drivers, the virtio transport running in the guest and the vhost transport in the host. About the vsock Linux drivers, the story of vsock in the Linux 3 starts in 2013 when the first implementation was merged with the vmci transport. Then in 2016, the virtio and vhost transport were added, And in 2017, it was also added the Hyper-V transport. These are the changes in the last year. We had 45 commits from 16 developers. I put some statistics per employer that regards the entire vSock subsystem, including the vSock core and all its transport, VMCI, virtio vhost, and Hyper-V. So these changes mainly regard fixes. We fixed several bugs, races, memory leaks in the core and the transport. But focusing on virtio vhost transports, in addition to the fixes, we also improved the performance with small changes that allowed us to gain throughput. What we did was to reduce the number of credit update messages exchanging between guest and host, and we increased the size of packets queued. So the first improvement regards the credit-based flow control implemented in the virtio vsock devices to provide reliable connection. Each peer stores these variables in the socket state and exchanges some of them with the other peer to update it about the status of the receiving queue. And these two variables are exchanged in every packet header or with an explicit message that only updates the credit available without carrying any data. So using local variables plus those received from the remote peer, we are able to reconstruct the status of the remote receiving queue, and we can calculate the available credit. In this way, we can stop sending bytes when we have no more credit. In the next slides, we will use this credit box that show the status of the credit. The white part is the available credit, and the red part is the credit already used. So in the previous implementation, the receiver, in this case the peer 2, send credit update messages to the transmitter every time the user consumes any bytes from the receiving queue. So a lot of messages were exchanged. To reduce these messages, we put a threshold, this line in the credit box, and that means that in this case the receiver sends the credit update messages only when the credit available seen by the transmitter, so the white part in the credit box, is less than the threshold. However, we continue to update the other peer when we have to send some data, because in every packet headers there are the fields for this information. The other improvements concern the sending path. In the picture, there is a sketch of the path that the packet must follow to be sent, starting from the user space to the device. So the vSock stream send message, the send callback in the vSock core, calls multiple times the virtio transport stream and queue to send the entire buffer coming from the user space. That's because the virtio transport stream and queue creates limited size of packet, and this limit was 4 kilobytes because this part of code is in common between guest and host drivers, and the host is limited to 4 kilobytes buffer pre-allocated by the guest. So in order to improve the throughput, we increased the size of the packet generated by the virtio transport stream and queue to 64 kilobytes, the maximum packet size handled by virtio vsock devices. And we changed the host driver to split large buckets according to the size of the buffer pre-allocated by the guest, which still are 4 kilobytes. This also allowed the guest to send up to 64 kilobytes packet directly to the host. We planned other improvements to explore, like tunable buffer size, mergeable buffers, but there is no time to discuss them now. So these two improvements were included in this patch, in this series, merged upstream, that will be released with Linux 5.4. During the development of the series, we discovered a huge memory usage with small packet in the guest when it receives small packet. And so we added a patch to limit the memory used, adding an extra copy to avoid this huge memory consumption. These are the results for the guest to host communication. So this is the throughput. The blue line is the reference, is the status before the series. The red line adding the extra copy for the small packets. The green line reducing the credit update messages, and finally the light blue line using 64 kilobytes packet in the sending path. So they are cumulative. That means that the light blue line includes all the patch in the series. And we have a big boost, especially with the last change, because now the guest can send up to 64 kilobytes instead of 4 kilobytes directly to the host. These are the same result, but for the host to guest communication. As you can see here, we don't have the peak as in the previous results because the guest is still using 4 kilobytes buffer pre-allocated by the guest. But we can see a better improvement thanks to the reducing of the credit to update messages. These are some, okay, we can talk about now about tools and languages that support vsock. On the left, we have useful tools that introduce the vsock support in the last few years. With this tool, we can dump traffic statistics. We can test the host-to-guest communication. We can access block devices using NBD and vsock. Or we can measure the performance with hyperv. On the right, we have some of the languages that allow us to write application using vsock sockets. So they mainly provide the binding for the vsock addressing. These are the next steps that we want to follow. First of all, multiple transport to support nested VMs. I have the other slides to talk about that. And another step is network namespace to create independent address domains that could be useful, for example, to partition VM in different domains, or in a nested VM environment to isolate host application from guest application bound to the same port. Another step could be the usage of virtio-net as a transport of virtio-vsock to avoid to re-implement features already done in virtio-net, like mergeable buffers. About the nested VMs, the problem that we have now is that the current implementation allows only one transport module loaded at runtime. So in a nested VM environment, we can't load virtio transport and vhost transport together. So for this reason, we need the MultiTransport support. I already sent some patches upstream. I'm still working on it. But in this preliminary implementation, we are allowed to load the vsock core regardless of the transport. And now the core is able to handle two types of transport. The host-to-guest transport that handles the host part in the communication. And in this case, in the QEMU KVM case, is the vhost transport. And the other type of transport is guest to host that handles the other part, so the guest part in the communication. And in our case, is the virtio transport. Each stream socket is assigned to a transport when the remote CID is known. And because we are using the remote CID to decide which transport to use. And it happens during a connect because the user specified the remote CID to connect to, or when we receive a connection request on a listener socket, because in this case, the remote CID is the CID of the requester. Listener sockets are not bound to any transport, so they can be created also if the transport are not loaded, or using vmadd cdany to listen on all transport. Concluding, vsock is starting to be used and well supported, and we are trying to improve the vsock core and virtio and vhost transport to make it more robust and performing. Question? I don't know if.
Could you go to slide, I think, 24 or 23? Oh, sorry, no, that 25, actually. So just a very quick comment. FIO now has support for libmbd. libmbd has support for vsock. mbdkit has support for vsock and for RAM disks. So you can now use FIO to test performance between your host and guest using MBD, which is extremely efficient. I now have one question as well, which is you can't have two vSOCs on the host, one listening and one connecting. They don't connect to each other.
Do you mean loop back?
Yeah, like a loop back between two host vSOCs.
Yes, it is an limitation because for the problem is the nested VM environment. So we don't have any, for now, any address to say, okay, this is a for loopback. an idea could be to introduce a loopback address, because for now the only way is to use, for example, in the host, use the host CID, but it could not work on the nested VM environment because the L1 cannot reach the L0. This is the reason.
I mean, that makes it very hard for us to actually write tests without launching a VM. Okay, thank you.
Yeah.
Quick question. What is the status of Windows driver support for vSock?
There is a GitHub with the KVM drivers, and there is the serial, but it's not vSock available till now. So yeah, that's what I know about, and I've been looking as reference on the Windows side. And I think that was like discussion with the maintainers there, and we could add that, but there is no like traction of why we could use that, so that we have several use cases and convince on that side, so that will add also support on vSock. Yeah, but that's what I know for now. Thank you.
What is about different transport in host? If different transport by type, if some VMs are running VMware and communicate via VMware transport, some transport running Microsoft with VM-bus transport, and Linux guest with virtio at once.
Yes, we plan it as a future work. We thinking about it, but for now there is no support for this case.
So it's more like Linux to Linux implementation. So we have a Linux guest and also on the host guest.
You mentioned that in the beginning to use vSock to communicate between two guests and not between guest and host. I actually think that
could be a use case, but the primary use case is available
I know
now.
that the primary use case is guest to host, but I was actually asked by several people, can we have some kind of configuration-less communication between guests? Because other hypervisors seem to have this kind of functionality, and it would be really cool to have just use the CID and that you have some kind of known guest that can trigger some action in some service.
I know that was an implementation from VMware, from VMCI before, but it was like get down because could be a potential attack surface between the two guests. So there was an implementation there available, but it was like not available anymore. So that's why I also take this into discussion, because this could be done, but it's additional implementation in addition from what's now available in upstream. Yeah.
Yes, and the other problem is the nested VM. So we can think about vSock as a point-to-point connection because we are not acknowledging in routing or something like that. So we are using the VM, the remote CID, to know if there is a nested VM or the host. This is the other problem.
Yeah, so someone talking to a CID other than the host needs to have this packets route to the other. So the current implementation doesn't know to do that.
Hi. On the slide about the Unix domain sockets, the graph, the performance compares various TX buffer sizes.
Yep.
And I didn't quite understand. So is that TX buffer size, is that the Unix domain sockets send buff, like sock opt? Is it the kernel, host kernel? Is that the buffer size?
It's in the Firecracker VMM. When you have the packets from the virtio-vsock device, if the host cannot cope to get that packet immediately, there is a ring buffer available so that we can immediately, when we receive the packet from the guest side on the virtio-vsock device, we process it. And if the host cannot get the packet at that time, we push it in the ring buffer, and the ring buffer is of this TX buffer size. So it's on that path. On the receive path, there is no ring buffer because we send directly the data from the Unix domain socket stream in the RX buffers of the virtio-vsock. Yeah.
So do Unix domain sockets not support send buff? Because it seems the kernel already has this functionality, and if you also reflect that buffer size in the credit mechanism, then I guess you would maybe never end up in the situation where the guest will send more than you're prepared to receive.
Then the host can be able to receive, yeah. And if we cannot cope with that, we enqueue that packet and that data and can be processed later. So
okay, I understand.
That could be that possibility. And actually, when I've done the performance evaluation, if I did not get the socket and the receive buffers on the host side high enough, I would have had less performance, less throughput, because it would have been impacted by the buffer size.
Okay, thank you.
Yeah.
Looks like no more questions, so thank you.
Okay, thanks.
Thanks for your attention.